We're now going to exam questions regarding logarithms and exponentials. The first question is this one. This is from 2009, paper 2, 2009. This question over here. Given that 1.25 to the power of x equals 2.5 to the power of y, use logarithms to find the value of x over y, this ratio, correct to three significant figures. So here you have, basically this is an equation, and you have to use logarithms. It actually tells you what to do in order to get this ratio over here. So how should you use this? It really doesn't matter what base you use the logarithm to solve this question. I used it's not this question over here, it's this. I used the natural logarithm, if I'm not mistaken. Yeah, that's what I did. So I use the natural logarithm. I apply to both sides of the equation, and then I use the rules of logarithm to figure out the value of the ratio x to y. Once I apply the logarithms, I can use the rule according to which the exponent, the power, can go outside of the logarithm. And then I just do what they are asking. I just leave this one over here. I bring the y over to this side. I send this one to the other side. I plug this in a calculator, and I provide the answer up to three significant figures. So here we have a very basic question, 3 points that you could solve in literally under 1 minute. Another one. This one over here. Solve correct to three significant figures the equation e to the power of x plus e to the power of 2x equals e to the power of 3x. About this time, every time you see something like this, a bell should ring in your head. One that tells you that this can be transformed into a quadratic. So this is a quadratic in disguise. Let's see how. You can easily transform this to an equation in which you have the same base, which would be e to the power of x. So this stays as it is. This one becomes e to the power of x squared. And this one, once brought to this side of the equal, can be transformed into e to the power of x cubed. So you can see here that if you do a change of variable in which the new variable is going to be e to the power of x, you'll have here something which is going to be a cubic. Not a quadratic yet, but a cubic. But you can transform this into a quadratic if you factorize this. That's what I did, even before doing the change of variable. So I factorized e to the power of x. What do I have left? Here I'll have 1, here I'll have e to the power of x, and here I'll have e to the power of x squared equals to 0. So I have now two factors. If you have a product of factors equal to 0, means that one of these factors at least must be 0. So I can do it like that. E to the power of x equals 0, or all that stuff equals 0. Now, can the exponential function ever be 0? Actually, the line y equals 0, it's an asymptote of the exponential function. So it can tend to 0 if x get a very, 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 very small, the negative side, but it can never reach 0. So this is impossible, which leaves us this to solve. And now we can do the change of variable that I mentioned before. E to the power of x equals u. I call it u. You can call it whatever you want. And then what is this going to turn into? Into this, which is a very simple quadratic. I just multiply the whole thing by -1 so that the coefficient of u squared is a positive constant. And then I solve this. I'll just use the quadratic formula in this case, and I'll get this value. If I use the minus, I will have a negative number over here, right? So if I undo the change of variable I did a little while ago, I will end up with this. This is a negative value. This is a positive value. A little while ago, I told you that e to the power of x could never be 0, let alone a negative number. So this is impossible, meaning that the solution is that one. So I want to get the value of x. So x equals the natural logarithm of that stuff over there, which, correct to three significant figures, is 0.481. A little bit more tricky than the previous one, but still not complicated at all. Let me see the number of points you have here, 5. Okay, it wouldn't be under 1 minute, but under 3 minutes you could solve this, and you'd have 5 points. Let's see the last one. This one, also 5 points. You are given a graph where sometimes this happens. This graph over here, in which you have natural logarithm of y over here, and here x. And then you have a straight line, and here the coordinate of 2 points. This is on the natural logarithm of y line. X value is 0, and then you have those 2 coordinates there. It says, the variables x and y satisfy the equation y equals a, open brackets, b to the power of minus x, where a and b are constants. The graph of natural logarithm of y against x is a straight line passing through the points 0, 1.3, as I mentioned before, and 1.6, 0.9, as shown in the diagram. Find the values of a and b, correct to 2 decimal places. So how do we solve this? The graph tells you what to do, because what do you have here? You have an equation of y against something, right? And this, on this diagram, what you have a natural logarithm of y. So the first thing that you should do is to apply the natural logarithm to both sides of this equation, so that you have on this side natural logarithm of y as required. And then let's work this out to see how we can get just x out of it. So this is what I did over here. Natural logarithm of y equals natural logarithm of all this stuff. If you have a logarithm of a product, this is going to be the sum of the logarithms. So the natural logarithm of y is going to be equal to the natural logarithm of a plus the natural logarithm of b to the power minus x. And then you know that if you have a power under a logarithm, you can bring it out and put it as a product of that power with whatever is left there. So what happened here? I brought the minus x over here. So I already have what I had a little while ago. On this x, it's already here. Everything that is in front of it is going to be the gradient. So this is the minus logarithm of b. The minus logarithm of b is going to be the gradient of this line. Why a line, by the way? I hope you notice. This is the equation of a straight line. Here you have whatever you have on the y-axis, which is natural logarithm of y. Here you have the x. What you have in front of x is the gradient. And the natural logarithm of a that we got a little while ago is going to be the y-intercept. This is the equation of a straight line, right? So the gradient is minus natural logarithm of b, and the y-intercept is a natural logarithm of a. And we can use this to get the values of a and b as asked. So how do we get a gradient? You know this for a long time. You are given the coordinates of 2 points, so you do the change of height over the change in distance. 1.3 minus 0.9. Actually, I use the other way around, so 0.9 minus 1.3 over 1.6 minus 0. This is minus 0.25. So, and the y-intercept is 1.3, is stated there. So you can very easily set simultaneous equations using this to get the two values. Actually, this is not even simultaneous equations. I just put them in two consecutive lines. So minus natural logarithm of b equals minus 0.25, and natural logarithm of a equals 1.3. and you do the opposite of the natural logarithm. Here you have two negatives, they cancel out. So b equals e to the power of 0.25 and a equals e to the power of 1.3. Plug it in the calculator, and here you have the two values correct to three significant figures.